session on fluid mechanics. In this session, we are going to take up the topic of surface tension. This is a very basic concept of physics, and hence we need to study this because it is applied to fluids, that is, liquids and gases, which are in contact with each other. It is defined as the tensile force acting on the surface of a liquid in contact with a gas or on the surface between two immiscible liquids such that the contact surface behaves like a membrane under tension. So you can have two examples here. One, we will talk about liquid in contact with a gas, that is, say, water in contact with air. Or you can have a surface between two immiscible liquids. Immiscible means two liquids which do not mix into each other. And there'll again be a surface contact between the two. And there'll be a membrane, a differentiation which will not allow them to even mix with each other. So we can take example of water and oil. The magnitude of this force per unit length of the free surface will have the same value as the surface energy per unit area. It is denoted by Greek symbol sigma. So we can use sigma as a symbol for indicating surface tension between two fluids. In SI unit, it is expressed as Newton per meter. The reason is it is surface energy per unit areas unit, which I am using here. So it will be Newton per meter. Now let's take up this example over here to understand the concept of surface tension. This is a free surface of liquid, as you can see I have shown here. Now this is say water. Above this we have air. So you can see I have shown the symbol for water with these dashed lines. Now we are talking about three molecules, A, B and C. First we'll talk about this molecule A. This molecule is well inside the surface of water. It's all water around here. So this molecule A is much below the free surface. This molecule A is subjected to forces on all the sides. As you can see here, it's being pulled on all the sides. So this A is actually very balanced because all the direction forces applied, so they cancel out each other and it is very much balanced, and that is why this molecule is much below the free surface and it is going to remain here until and unless it experiences some kind of pull in the upward direction or more pull in the downward direction. Now when we talk about molecule B, it is somewhat at the surface of the liquid. So when you look at molecule B, you will understand that it is exerted upon by more forces from the downward direction as compared to upward pull. But this molecule will remain suspended here till this upward force is able to hold it. When this downward force becomes more, it will directly come down and be somewhere around this molecule A. This B is having an unbalanced force from upward and downward direction. The pull is a little bit of unbalanced. When I talk about molecule C, you can see here that it is unbalanced with a pull in the downward direction, but this top surface is acting like a stretched membrane. It is keeping it held at that surface, and this C molecule will not go down. It will remain suspended here only. The reason is it is experiencing an equal amount of force from the top direction also. So it will remain suspended here, it won't go down until and unless a more amount of force is exerted in the downward direction and it has to move down. So all the molecules like this molecule C at the top surface will form a stretched membrane, and this membrane is nothing but the phenomena of surface tension because this molecule is completely under the effect of tensile forces. It is in tension. So that's the basic concept of surface tension, and it is like a stretched membrane at the top. Now let's discuss a derivation of surface tension on a liquid droplet. We will consider a small spherical droplet of liquid whose radius is say r. So I'll show you a droplet whose radius is r. On the entire surface of the droplet, the tensile force due to surface tension will be acting. So we will cut this droplet into half. So it is something like this that I am cutting it into. So when I take this droplet outside, you can see here, this is a droplet, and on this surface there will be surface tension. That's sigma. So I'll show you, this is surface tension. Also, there will be pressure force exerted inside the droplet. So I will show that over here. This is the pressure force exerted on the droplet. So I have drawn three figures, 1, 2, and 3. Now here we are going to talk about sigma, which is the surface tension on the liquid. As you are aware of it, the diameter of the droplet will be say d, and when I talk about the pressure force, which is inside the droplet, and this will be indicated by p. So these are the three terms that we are going to require. So suppose if I talk about the forces which are acting on half of this droplet, will be the first force which is acting will be the tensile force due to the surface tension, which will be acting around the circumference of the droplet. And if I have to write an equation for it, this will be equal to sigma into the circumference. So that will be nothing but sigma into pi d. So let me mark this as equation A. Now the second thing that will be acting is the pressure force which is inside the liquid surface. So this pressure force will be nothing but pressure into area. And area over here will be pi by 4 d square. It's a cross section area. So this is my equation B. Now when I equate A and B, for equilibrium condition, obviously, this will be sigma into pi d is equal to p into pi by 4 d square. This pi gets cancelled out, one diameter gets cancelled out. So therefore, I can say that pressure over here will be 4 sigma upon d. This equation is valid for surface tension on a liquid droplet. So as the diameter is going to decrease, you can say that the pressure inside the droplet will increase and vice versa. So this is about the liquid droplet. Now let's talk about the surface tension on a hollow bubble. Now when I talk about a bubble, it is exerted with pressure on the outside and also on the inside because there will be air on both the sides. So for this type of condition, you can say that the equilibrium condition will be P into pi by 4 d square because that is the pressure exerted inside the bubble. But there is circumference outside and inside both, which is subjected to air. So here we will just take this as 2 into sigma into pi d. So now if I cancel this out, one diameter, so therefore pressure becomes 4 2s are 8 sigma by d. So this is the equation or the relation between pressure, diameter and surface tension for a hollow bubble. So that's all about surface tension. I hope you have understood the concept. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session with numericals on surface tension. Thank you.